So hello everybody and welcome to the last session, to session 6 of the ISS conference. It's my great pleasure as the session chair of this session to introduce 5 interesting papers and presenters to you. My name is Raimund Dachselt. I'm heading the Interactive Media Lab at the University of Dresden, Technische Universität Dresden. And without further ado, let's start with our first paper presentation, which just before we start, I would like to encourage you to use the Discord channel. I forgot to say that, to post your questions to the respective paper. One of each of the 5 papers has a separate channel. Please post your question there and we will answer these questions, and the authors will answer the questions after the subsequent presentations of their papers. All right, so it's my great pleasure first to announce Mehdi Osmer from Université Catholique de Louvain in Belgium to present the paper Recognizing 3D Trajectories as 2D Multistroke Gestures. So I hope you're ready, Mehdi, and the floor is yours. Please go ahead.
Thank you very much, Raymond. So now I will share my screen. Okay, is it okay? Do you see my screen? So hello everyone, my name is Mehdi Osmer and I'm a PhD student from Université Catholique de Louvain in Belgium. Today I have the pleasure to present our recent work, Can we recognize 3D trajectories as a 2D multi-stroke gestures? I will start with the introduction and then I will move on to the other parts. In a previous gesture elicitation study, we asked participants to elicit gestures that fit actions and commands to control objects in an IoT environment. As we can see in this video, some participants elicited 2D symbolic gestures in thin air. In the 3D space, we can represent gestures as sequential data of single point. In the literature, we call this kind of gestures trajectories. Moreover, I would like to mention that there are several gesture recognizers for 2D or 3D gestures based on different techniques. And for that reason, we raised in this work the question, can we recognize 3D trajectories as a 2D multi-stroke gestures? Now I'd like to move to the challenges that we face to answer the question. After conducting a targeted literature review on 2D stroke gesture recognizers, we selected 4 of them for multiple reasons, but mainly because they are simple as well as well-known recognizers. We cite Rubin's algorithm, $P, $Q, $P+. Next, we extended less recognizers to 3 dimensions and got 7 3D recognizers. First, Rubin 3D is formed of 3 2D Rubin's recognizers. Second one is Rubin Chang, an extension of Rubin's recognizer to 3 dimensions by adding the Z coordinate. The $family recognizers are extended to 3 dimensions by adding the Z coordinate. $P cube and $Q cube both are 3D versions of $P and $Q respectively. $P plus cube is the 3D version of $P plus. $F and freehand uni are 2 new variants of $P. $F is an improved version of $P cube with a flexible cloud matching of $P plus. The freehand uni differs from $F because the early abandoning is not included. To prove the efficiency of recognizers, thus we experimented them in both user-independent and user-dependent scenarios, using 3 trajectories datasets. Furthermore, we tested recognizers for different conditions defined by 2 variables, the number of templates and the number of points, or sampling. We collected the test results through 2 quantitative measures, the recognition rate and the execution time. Also, we could analyze the effect of the 3 factors on measures, which are the dataset, the number of templates, and the sampling. Now I would like to draw your attention to the total number of recognition trials performed. which is in total 665,000 recognition trials. During this experimentation, we used 3 datasets. The first one is the Shrek 2019, a recent dataset with 5 gesture classes. The second is the 3D MATLAB SD, which is composed of 4 subsets or domains with in total 40 gesture classes. And the last one is the 3D TCGS with 26 gesture classes. Sorry. In the next slide, we present some examples of graphics and tables. They are produced from the test results on each dataset for diverse conditions. We generated a normalized balanced confusion matrix for $P plus Q. We also plot individual results for different conditions. In this slide, we can examine the average recognition rate for each recognizer on all datasets. In this diagram, as you can notice, $P plus Q has the best recognition rate with 87.48%. $P plus Q may have a higher recognition rate. It depends on which dataset the recognizer is evaluated. For instance, with some datasets, the rate can exceed 90%. In the middle of the graph, we remark the $-like recognizers, which have a similar rate and which is around 80%. At least we can observe that the Rubin 3D and Rubin Chang have low recognition rates under 70%. The Shrek 2019 and 3D TCGS datasets are evaluated only in the user-independent scenario. And from what we view in test diagrams, the recognition rates are similar to the average recognition rates seen in the previous slide, except for the Rubin 3D and Rubin Chang. In this slide, we take note of the difference between scenarios. We observe a loss of nearly 10% for $P plus Q and around 20% for the other $-like recognizers from user-dependent scenario to user-independent scenario. In these diagrams, we notice the low rates of all recognizers for the domain 4 in user-independent scenario. And the principal cause is the type of gestures in this dataset. This figure indicates the recognition rates for all recognizers on the MATLAB SD in both scenarios. We remark significant differences when switching from user-dependent to the user-independent scenario, though there are some exceptions. Based on the results of the evaluation, we can say that the $P plus Q is the most efficient and effective recognizer most of the time. Rubin Chang should be avoided due to its low recognition rate in all conditions compared to the other recognizers. Concerning the effect of factors on measures, we cite the effect of the number of templates on the recognition rates of all the recognizers, the significant effect of the number of points on the $-like recognizers, and likewise, the datasets affect the recognition rates for all recognizers in the user-independent scenario. To sum up, we made 7 3D gesture recognizers based on 4 2D recognizers selected from the state-of-the-art. We implemented the testing framework in JavaScript and tested the recognizers. The test results showed that the $P plus Q provides excellent results. We have a list of some improvements for future work. We would like to propose the effect evaluation of the depth variation in gesture. Moreover, we would suggest to compare with other recognizers based on other techniques. And finally, evaluate more complex gestures. Thank you for listening.
Yeah, thank you very much. I don't know whether I'm...
You're welcome.
I have to start now, right? All right, thank you very much, Mehdi, for this interesting presentation, and congratulations on this really thorough and deep work, which is a good foundation. Let's come to the questions later on. Please post them in the appropriate Discord channel, and we move on to the next paper presentation, which is the paper is presented by Bruno Frischer from now Saarland University. I hope I get it right. And Bruno will talk about side-crossing menus. I don't read the entire title to you. Side-crossing menu, a new way of having gestures, a larger set of gestures on very small surfaces. Thanks a lot. and go ahead. Please, the floor is yours.
Thank you, Ramon, for the introduction. So I am Bruno Fruchard. I am from the HCI lab in Zaren University. And today I will be presenting side-crossing menus enabling large gesture sets on small surfaces on behalf of my co-authors, Eric Le Collinet and Olivier Chaput. So in this project, we were interested in small wearable surfaces like the smartwatch you can see here. And we were interested in two aspects of them. First, they are wearables, so they enable the user's hands to be free all the time. And most importantly, we carry them with us all the time. Meaning that when we are switching between different interactive environments, like working with a mixed reality headset or working with devices at home in an IoT environment, we have this device. So we were wondering, could we use such a small device as a controller for controlling various environments and switch between them fluently, seamlessly? So what, for instance, if we could control one unique smartwatch to control a mixed reality headset and mixed reality environments, use the same smartwatch to control IoT devices at home, and use again the same smartwatch to control large displays. So in other words, the strategy we want to use here is use one smartwatch to rule them all. So the main challenge in this is that we need large gesture sets to control all these types of all these different environments. But the input space, the screen of a smartwatch is rather limited. So for this, our solution, what we propose is a new gestural interaction technique called side-crossing menus that relies on position-dependent and path-flexible gestures that enables a novice and expert modes, enables also eyes-free interactions, so the user can focus on the main task and not looking at the watch. And importantly, I will go back on that later, it relies on broad and shallow menus. So I'm going to go through all those points by explaining to you the interaction design of the technique. With SCM, it relies on a grid layout, as you can see here, and it consists of three main components. An SCM gesture consists of three main components. First, a starting cell. Second, an ending cell, which makes it position dependent. And the side crust of the ending cell. We consider the side crust here of the ending cell to create a large number of gestures and to be able to support a large number of gestures. So two things are important here. First, all the gestures start from the sides, so from the bezel of the smartwatch, which is a way to support eyes-free interaction. And the second thing is gestures can start from the same starting area, which for users to learn the gestures, and this novice mode is displayed on auxiliary displays. So since the smartwatch is again very limited in terms of input space and visual information, we display them on other displays in the environment, like the mixed reality headset or large display. So here you have 8 menus on the bezel of the smartwatch. To open a menu, the user just presses on this menu, then can see all the different commands she can select and perform an SCM gesture. What's interesting with SCM is that it's path flexible, meaning that the user can perform different paths to perform exactly the same gesture. So it enables the users to be free to decide on the strategy they want to use and also correct, if they did a mistake, the path of the gesture. Now, SCM also supports eyes-free interaction. For that, we use two different types of tactile aids. First, active vibrotactile aids when the user is drawing a gesture on the display. Here, every time the user enters a new cell, there is a burst, a small vibration to indicate she entered a new cell. And we also use passive tangible aids on the side of a smartwatch, the dark gray area you can see here. With our prototype, we use paper stickers for this. And the point is to indicate the starting cells, so the user will not make a mistake when performing SCM gestures without looking at the watch. The last aspect I want to talk about with SCM is that it's using broad and shallow hierarchy of menus. Here you can see we are using only 2 levels. There is one level for menus, we use 8 menus. And then the second level, a menu will consist of 21 to 22 items. This type of hierarchy is contrasting with the more conventional deep and narrow hierarchies of marking menus. For a marking menu, you would have only 8 items per level, meaning that if we want to reach the same number of gestures, with SCM, we enable 172 gestures on a smartwatch. With marking menus, to reach the same amount of gestures, we will need 3 different levels, and we will reach 160 gestures. So in the experiments I'm going to present right after this, we compared SCM to the marking menus. We performed 2 experiments. The first one focused on the usability of SCM, and the second one focused on the learnability of SCM. For the usability, we performed the experiment with 12 right-handed participants, where we wanted to answer how fast can users master SCM and how efficient are SCM gestures. Here we focused on the expert mode, meaning eye-free interaction. The user could not look at the watch. And the task was simply to perform SCM gestures as accurately as possible. The only visual information the users had was the starting area, the ending area, and the side to cross. The results from this experiment is that users can be very accurate with SCM after 20 minutes of practice, which is quite fast, so they master the technique quite rapidly. The selection times of this technique was in average 3.5 seconds, which is rather long, but you have to consider these were novice users using eye-free interaction. And we observed that the participants used various paths, even though they were not instructed to do so, to perform exactly the same gestures. Here's an example. What you can see here is each line is the path of a user. And this is exactly for the same gesture. So you can see they use different strategies. Now we did the second experiment on the learnability of SCM, and we compared SCM to marking menus. For that, we had 12 participants, new participants, other participants. And the question was, how easy are SCM gestures to learn? And do shallow menus, so the hierarchy of SCM, facilitate learning over deep menus? What we found in these experiments is we did not find any significant difference between, in terms of accuracy and in terms of speed between the 2 techniques, which we interpret as the 2 types of hierarchies yielded these comparable results. So we interpret that as SCM is a good alternative for designers as marking menus, so it provides another type of hierarchy. Thank you a lot for listening, and I'm really looking forward for any questions you might have.
Yeah, thank you very much, Bruno. And I can still switch. Can I switch on my video, please? Now I can start it. All right, thanks a lot, Bruno. This is very interesting work, and I'm happy to discuss it later on after we have seen all these remaining 3 presentations. And I encourage everybody who is attending this session now, session 6 of ISS 2020, to post their questions into the Discord channel if possible, so we can later on ask them. Now, the third paper will be on recognizing textures in the wild, so bringing them to reality. And this paper is presented by Adnan Guetaf from the Université Polytechnique Hauts-de-France, from France, obviously. So the floor is yours, and we are looking forward to your presentation.
Hello, thank you. I will share my screen. So, hello everyone. My name is Adnan Guetaf, and I'm a PhD student at Université Polytechnique Hauts-de-France. Thank you for listening to this presentation titled Effect of Physical Challenging Activity on Tactile Texture Recognition for Mobile Surface. This work was conducted by me, Yusra Rakik, and Laurent Grisoni. Sorry. We will begin our presentation by the motivation that inspired us to conduct this work. Interacting with touch device allows users to directly manipulate digital elements through touch, and recently allows to perceive touched objects through tactile feedback. Several approaches have been proposed to enhance haptic capabilities in touchscreen devices using 2 main technologies that are electrovibration, which enhance the friction between the surface and the user finger. And on the other hand, we have ultrasonic technologies, which reduce the friction using squeeze film effect. Also, previous research on tactile texture recognition demonstrates the ability for users to accurately recognize texture, even when using different finger speeds, or when perceived as simultaneous but different texture, or when the size of the tactile texture is small. Researchers have also proposed different applications to strengthen the interaction or to enhance the expressiveness of touched objects, or to offer accessible interaction designed for people with impairment. However, all those studies were evaluated in the lab setting where participants had to focus only on tactile feedback-based tasks, which limit the overall generalization of those findings for other more realistic scenarios. Like, for example, when we are standing, walking, or even being on public transport, where user attention can be directed toward another task that requires certain attention or visual load. Now I will explain the experiment section. We conducted an experiment to evaluate effect of physical challenging activity on user perception of tactile texture. We consider 5 challenging activities that we think represent common situation where users often use their smartphone, which are seated in the office, standing in the office, standing in the tram, seated in the tram, and finally walking. 12 participants volunteered to take part in our experiment. All the participants used smartphone for at least 5 years with a daily use in different context situation. We used the Evita device for this experiment, a tactile feedback tablet that supports friction reduction by means of ultrasonic vibration. We consider here for tactile texture. We encoded the different texture with respect to different texture densities from the densest one to the sparse one. And by alternating high and low friction, here high friction is associated with the black color and low friction with the white color. The set of considered texture was used in previous research and proved to be distinguishable by users. Now I will present the results. We present here the quantitative results for each of the dependent variables: accuracy, recognition times, number of swipes, and number of clutch. For the accuracy, which here represents the portion of correct identification of texture, we can notice that there is a significant main effect of activity. Post-hoc tests revealed that when walking in the street, the performance were deteriorated significantly compared to the reminder activities. For the recognition time, which represents the time taken by the participant to sense and recognize the texture, we observed a significant main effect also of activity with walking being significantly slower than both seated in the office and standing in the tramway. For the number of swipe, which is defined as the number of times the user uses his finger on the surface from left to right or right to left to recognize the texture, we found that walking produced significantly more swipe gesture than standing in the tramway, with no significant difference with the reminder activities. And finally, for the number of clutch, which represents the number of times the user removes his finger from the surface and put it again, we found no significant difference. Overall, we also observed that walking in the street deteriorated the performance compared to the reminder condition by 8%. For the qualitative results, most participants felt that when walking in the street, identifying the perceived texture is harder and more mentally challenging than when being in the reminder activities, which was correlated with the user response to the NASA TLX questionnaire and the participants' remark collected during the experiment. As we can see, that one clearly stated that it was more difficult for him to manage two tasks simultaneously, which are working and performing the experiment. And another stated that when walking, I had difficulties sometimes to differentiate between the 4 textures due to the physical activity. In contrast, participants stated their satisfaction in recognition to texture when being in the office or in the tramway condition. For the office environment, one participant said that when being in the office, I'm more sure about my touch senses and choices, and I can easily distinguish the different texture. And another stated, for the environment context, as I use always my phone in the tramway, I feel confident about my responses. To summarize our results, we found that both posture, here we have seated and standing, do not impact the performance in both static and dynamic environments. We found also that being in a dynamic environment do not necessarily impact recognitions, as we did not find any effect on either accuracy or recognition time. Our result also showed that that walking in the street had an impact on recognition rate. We observed a decrease of performance up to 8.45%. However, even if it looks at first glance that it may look like using tactile texture while walking in the street is unusual, the recognition rate did achieve a good rate of almost 83%. Consequently, this suggests that tactile texture could be effectively recognized and used by user when walking in the street. And as future work, we consider the study of more challenging or different posture, like lying down, for example. Also, our result cannot be generalized for other vehicle contexts which might have different traveling speed or can produce more or fewer jitters that are likely to be the reason why tactile recognition can increase in difficulty. Also, for the street context, we consider only the walking activity, so the results remain uncertain for other activities like running or working with different walking speeds. Thank you for your attention.
Yeah, thanks a lot.
Thank you.
Adnan, and Right, thanks a lot, Adnan. And again, very interesting work. Please post your questions in the Discord channel, in the appropriate channel for this paper. And we are happy to discuss and see your questions answered after the remaining two presentations. The next one will be Subtlety, Augmenting Posture Awareness for Beginner Golfers. And this work will be presented by Nikolai Wozniak. And I hope there is no direct connection to the recent elections, but this was maybe just a bad joke to kick it off. So please, the floor is yours, Nikolai, and go ahead. Oh, and
Thank you very much.
He's from Lodz University of Technology in Poland. Sorry, I forgot.
Thank you, Raymond. Try to share my screen now. Good. So good afternoon, everyone. My name is Mikołaj Woźniak, and today I would like to share with you the results of our work on augmenting posture awareness for beginner golfers. This project was held by Łódź University of Technology in cooperation with Utrecht University and VU in Amsterdam. So the game of golf becomes more and more popular worldwide, providing the benefits of light physical activity to millions of recreational players. However, golf requires extensive training before it can be fully enjoyed. Maintaining control over one's body and the club's swing line is necessary to reach the desired performance and fun from the game. We consulted professional coaches as well as competition and recreational players to understand the struggles of beginner golfers. Through a series of interviews, we established that proper posture prior to the swing is crucial for maintaining accurate club trajectory. Beginners tend to struggle with finding the right balance on their feet and keeping the elbow of the leading arm straight, which prevent them from taking a clear shot. However, great majority of golf-related research in HCI focused on club-related parameters of a golf swing, especially mapping its trajectory and rotation along the swing line. Commercial systems for golfers follow this trend. Few solutions which offer posture analysis are designed in a way that is unsuitable for amateur players. The measurement and analysis provided by these systems are difficult to interpret without help from a pro, and the devices themselves are often just too costly for recreational players. Therefore, we aim to address this challenge in a way that would be designed with the beginners in mind. Based on our initial analysis, we formulated two main research questions. We wanted to study whether a real-time feedback system can aid beginner golfers in adjusting their posture and try to establish what is the optimal modality for providing posture feedback. We initiated a user-centered design process to create a prototype that would enable us to explore these questions empirically. So we created Subtlety, an interactive driving range post capable of providing posture feedback for golfers. Since we aimed for high ecological validity and synergy with existing training facilities, we decided to equip a standard driving range mat with pressure sensors installed on the player's feet. The system assessed relative differences in players' weight balance and guided the player to keep the proper posture when preparing the shot. To aid the beginners with keeping their elbows straight, we provided a simple wearable device to monitor its state. A sports sleeve equipped with a flex sensor was provided, together with a control feedback unit that was attached to a custom end phone holder armband. We designed 3 different feedback modalities for Usability: audio, visual, and vibrotactile. Audio feedback used a frequency-based metaphor to indicate balance disruptions, similar to the one used in parking sensors. We used the near-field speaker arrangement to play the cues to the player. Visual feedback was provided using in situ LED displays and color coding, while vibrotactile stimuli were provided using wearable bands on players' calves. To investigate if Usability can aid beginner golfers in adjusting their posture and to determine what modality was most suited for the feedback, we conducted an experiment with 20 participants. We deployed Usability at a local driving range and invited beginner golfers to participate in a study where they took a series of swings. Our experiment design focused on understanding the effect of different feedback modalities. We examined 4 conditions. So no feedback, visual feedback, audio, and vibration feedback. The swing quality was assessed by professional coaches in post-hoc video analysis. We also analyzed the error logs from the device. Self-reported measures were used to assess systems usability and the cognitive load required to use it. Based on the coach assessment, we found that using Usability with either vibration or visual feedback resulted in improved performance. Moreover, audio feedback led to significantly more errors triggered when preparing for the shot. This means that it takes significantly more time to reach the proper balance with audio cues than while using different modalities. Vibration and visual feedback were considered more usable than audio feedback. Audio feedback was also rated significantly more frustrating than other arrangements. During the interviews, players claimed that they feel more confident and self-aware when posture feedback is provided. Many users expressed their willingness to use the system as a regular companion to individual training sessions. Beginners found such device useful for unsupervised training between regular classes with a pro. So, to sum up, we confirmed that our hypothesis that providing posture feedback to beginner golfers increases the quality of their swing. Considering the feedback modalities, it is not possible to indicate the optimal one, with both vibrotactile and visual feedback contributing to better performance. Audio turned out to be insufficiently usable and frustrating, leading to more errors in the body alignment. Our work contributes insights on using different feedback modalities, incrementing the previous inquiries. We believe that our results may be useful in designing supportive tools for various semi-stationary activities and sports. Thank you very much. I'll be glad to take your questions after the session.
Yeah, thank you very much, Nikolai. Very interesting presentation, and I hope that some of you now start playing golf with the help of this system. All right, so again, post your questions in Discord, and we will have an answer session and discussion after the last presentation. And the last presentation will be given by Paulo Diaz from University of Aveiro. And he will be talking about interaction with virtual content using augmented reality, a user study in assembly procedures. So the floor is yours. Please go ahead, Paulo.
Okay, thank you. So good afternoon. Horizontally, okay, wait, just 1 second. My Zoom. 1 second.
It looks okay, yeah.
It's okay, Paulo. I can
It's
see
okay.
it right.
It's okay now? Okay.
It's just
Okay.
a background picture which is flipped, but it's not important.
So is it okay? Are you seeing my presentation right now?
Yes, perfectly.
Yes. Okay, so let's go for it. So I'm going to speak to you about our paper that is interaction with virtual content using augmented reality and a user study that we have developed regarding assembly procedure. So the context and the motivation for the work is that augmented reality has great potential for all the application that has to do with assembly procedure. But the interaction in such a setup with augmented reality is not very easy, and it depends a lot on the different kind of gestures that we are using, if it's interesting or working well or not. So in this paper, what we decide is to evaluate 3 different methods for interaction in an augmented reality setup, and try to do a user test to see which one are the better and allow to do the assembly in the best way. So the 3 methods that we are testing is touch screen on a mobile phone movements, and an interaction in an HMD, a see-through HMD, also in augmented reality. So for the development, we use the Unity motor game engine that is well known, and then the different specific SDK that are necessary. For augmented reality based on the markers, we use the Vuforia library, and then since we also use the HTC Vive Pro, we use also the SDK from them. So coming to the 3 different methods that we are evaluating for interaction in augmented reality. In our case, the first method that we are using is the touchscreen gestures in a mobile device. So in this case, what we are actually doing is that we are going to move the objects we want to move in augmented reality by sliding the objects directly on the mobile phone's screen. So you can see this method here. So what's happening is I can select the piece I want to move, and the piece has to be moved to the position that I want, that is already shown in transparency. So in this case, the movement is done simply by sliding, by dragging the object on the mobile screen. And then you also have 3 buttons on the left side that you can see, in which you can adjust the Z coordinate, and you can also rotate the object, okay? So the idea is that I can actually move objects in an augmented reality setup. And in this case, the movement is done using the usual interaction we have with mobile phone, that is dragging directly the objects on the screen, okay? Since we are working in an augmented reality setup, we thought that it could be interesting to use a second method, also based on a mobile phone. But in this case, the idea is that instead of dragging the objects, we are going to anchor the objects to the mobile phone and move the object as we move the mobile phone. So actually, this is a real 6 degree of freedom interaction. We don't need any additional button, just for the selection. And so what's happening now is once I have selected the object, as you can see on the right position, I move the mobile phone and the objects will be anchored to the movement of the mobile phone. So if I want to rotate the object, I really have to rotate the mobile phone. If I want to go up or down or move on XY, I really need to handle and move the mobile phone with the object. So after selection, the object is anchored to the mobile phone and will be moving toward the position that I want, okay? And this is the second method that we have that is also using mobile phone, but in this case, I'm not using gestures, but really real movements of the mobile phone to do the movements. The last one is significantly different. We use it because we have an HMD available. So we wanted to try this with a method in which we have hands-free, or more or less hands-free. So the visualization is done directly on the HMD. And since we want to do this in an AR setup, just like for the other ones, what we've been doing is we've been doing video see-through through the HMD. So we use the HTC Vive Pro that has 2 cameras, and we use the cameras from the Vive Pro to provide video see-through augmented reality. So this is the same experience, but this case, this is done on the HMD. And on this case, the manipulation is doing by selecting the object with the controller, triggering to select and to end the object, and then moving the object to the right position, okay? As you see, the object has to be put in the correct position. And for example, if the rotation is not correct, it will not fit to the position as expected, okay? So this is the third method that we've been trying, okay? And then after implementing this method, what we've been doing is basically a user's test to try to understand which of the method is better or not, okay? So we've done a test with 27 participants. 17 of them already have experience with augmented reality. 7 have never used augmented reality before. It was a within group experiment, meaning that all the 27 participants have tried all the 3 methods, the 2 with the mobile and the 1 with the HMD. But to try to avoid learning effects, what we've been doing is we have changed the order. So the order of the experiment was split in such a way that all the different combinations were done the same times. And if one starts with a method, the other one will start with the other one, and so on, to ensure that there is no globally learning effect from the order. Okay? So the 3 methods that we've been trying, as you've seen, was the touchscreen, the left one, the C1, the C2, the gesture, that is the C1, the mobile, the anchor mobile phone with the movement, that is C2, and the controller and C3 HMD, that is the C3. Okay. The task itself was already shown on the video. So the idea is that the user has to do the assembly of a Lego brick car. The Lego brick car has 9 pieces that have to be collocated or put on the right position. Okay, so 9 pieces that has to be put in the 3-dimensional correct location. The piece that is actually selected is in green, and we have a predefined threshold in which if the pose of the piece I am moving is close to the final position below this threshold, then it will glue automatically to the piece. Okay, maybe I can just show in the video again, it will be probably easier. So the idea is once the piece is coming close to the right position, it just glues to the end. So the idea is that I don't have to do a very fine selection and adjustment, but when I'm close to the right position, it will just glue to the correct one. Okay. So regarding the results that we have, the main result that we have was that the HMD was much faster. So this is the overall time completion of all the users for all the experiments. And actually the HMD was much faster. The touch was slightly faster, and the movement was the longer one. So it took globally more time to do the mounting with this. We also notice, and this is interesting, that this is the time it took for each one of the pieces to be put in the position for all the experiments. So it means the blue was for the first Lego piece, the orange was the second one, and so on. Okay. So if you look at this, what we see here is that it looks like there's the necessity to learn the device movement, as the first movements with the first piece were much longer than the other ones, meaning that after a while it looks the user were much more efficient with the movement, but at the beginning they have some problems, probably because this is a kind of interaction they've never used before, whilst on the other one it's not exactly the same that was happening. So we have a post-task questionnaire also. So most of the participants, actually 26 out of 27, preferred the HMD position. But most of them also consider that the condition C1 and C2 are still usable and maybe a good compromise because they are not so complex and they are also much less expensive than the HMD position. So actually, this is a conclusion that we have. Some discussion about the experiment. The Lego car assembly task was probably very simple. So some of the results that we have are probably due to the fact that that task was very easy to do. And probably if we try to perform more complex tasks with more steps and more complicated one with some instruction, maybe the result should be a little bit different. We also have some problems with the HMD system because the camera of the HTC Vive is of low resolution. So there is a kind of discomfort. The image is not very good. And most of the users complained that after a while, they would probably feel some sickness and dizziness. So it was a problem that we also have with the HMD. Okay. So the global conclusion is that the HMD and the controller's condition was the fastest one and was the preferred. But it has some problems due to some technical issues like the low resolution, and some of the participants just report to have nausea and sickness, small ones. So for long periods, maybe it wouldn't be the best one. And the other thing that is interesting is it appears that the device movement might be interesting, but it might need some training, because for the first piece, actually, it was much longer to use than for the last piece. And probably after a while, user could use it probably almost as well as the gesture movement. For the future work, something that we are planning to do is to try to extend this to do some collaboration. So the idea that we can have different interaction is the idea that different people with different hardware could be collaborating in something like, for example, mounting a car track or something like that, that they can all collaborate together in gluing this in an augmented reality scenario. And this is it. Thanks all for listening to me, and let's go for some questions on these presentations. Thank you.
Yeah, thank you very much, and a virtual round of applause to Paulo and of course to all presenters. So this was really great to see all these 5 presentations here, and I still can't start my video. Now it works. So I think it's a good time to show their videos and to open the round of questions and answers. So thanks again. So if you have missed it, thanks again for this great work, for your nice presentations. I will start with the first paper. So I go a little bit in order to make it clear for everyone. And this is a question to Mehdi. And about could we use, that's an interesting one, your tracking methods basically to recognize also people's trajectories, not just hand gestures in 3D space, but maybe head movements, for example, of users, say in virtual reality or in some spatial interaction scenario.
Yeah, could you turn on my camera, please? I can't because, yeah.
That would be nice to see Mehdi as well.
Okay.
Here he is. Mm-hmm.
So can you repeat your question, please?
Yeah, the question was basically, you are tracking 3D gestures in space, but hand gestures, but this could also be perhaps used for tracking people's trajectories, like head movements, for example. Would you think your technique could be extended to also track head movements or other movements of people?
Yeah, of course, we can track any part of body. The only condition is to take a single point from this part of the body and track this point by recording the time at the same time. So we can apply the tracking and recognize trajectories for this kind of trajectories of person arm which are moving in 3D.
Right. Next question would be by Joachim, and he said, interesting work. I wonder if there could be different semantics for approximately 2D gestures and clear 3D variations of the same gestures. So would you make a difference between like dedicated 3D gestures or rather gestures which are more or less 2D? Does it make a difference?
I think it depends more in the sensitivity of the recognizer. So if, for example, if we take the dollar-like recognizers, they are invariant to order, to number, but not to the rotation. So if we rotate trajectories, it won't recognize it.
Mm-hmm. Okay. All right. And maybe last short question, did you think about extending that to, for example, bimanual gestures? So to also track 2 gesture parts at one which form together a gesture?
Excuse me, can you repeat?
Did you think about extending that to bimanual, so 2-handed gestures, which are a bit more complex than these single stroke, 1-handed gestures?
Yeah, of course we can, but it won't be the unipath unistroke. It will be multipath unistroke. So, but we can do it. Yeah.
Right, thanks a lot. And we need to move on a little bit to the next paper, to the side-crossing menus paper. You remember that? And Arnaud Pozot is asking here, what was the participants' position during this study? That means, were they standing or sitting? And could that have an influence on the performance if they are in a different position? Yeah, Bruno, maybe.
Yes, thank you for the question. So in the study, we only investigated participants seated. So they were sitting at the table. and they could lay their arm on the table or on their thigh. And we did not investigate them standing or moving, which actually is something we would like to do as future work. And we don't have results on that. My feeling is moving, yes, would make some disturbances and would lower the accuracy that we observed. But I feel that just standing, the participants could still take a position that would be stable enough so that the accuracy will remain unchanged. But we need to do some more tests on that to be sure.
Mm-hmm. Very good. And we have another question here. Again, people are congratulating you on this great work, like everybody in this session. I was wondering how memorable are the gestures? The original work on marking menus focused on learnability and memorability. So maybe you can reflect a little bit on that aspect of memorability.
So the second experiment we did was on learnability. And we also investigated how the participants could recall the gestures. We did that only on one session. So only one day, we don't know about the long term. But on the short term, we observed 80% of the gestures could be remembered after 4 blocks. So 4 times learning and then 4 times recalling right after it. And the participants had to learn 8 commands during this experiment. So for more details, I refer to the paper. Okay. I direct you to the paper. But yes, that's what we got in the second experiment.
All right, okay. Maybe just a very quick question. Would the shape of the device also influence the menu design? Like if you had a circular menu instead of a rectangular watch, for example?
Yes, it would. And this is something we also wrote as alternatives of the SCM design. So we could also use polygons as shapes instead of just rectangles. That would likely make the interactions then more complicated, more complex. But we could still use the sides of the polygons to do something. So on a circular device, we have some examples in the paper of shapes and layouts we could use for this. And we'd be super happy to investigate that.
Thanks a lot, great work. And we move on to the tactile texture recognition paper for mobile surfaces. Adnan, a question to you from Miguel Nacenta. He also said, thanks for the nice presentation. I wonder whether your data allows you to guess at what the actual cause of the difficulties are. Is this a matter of the movement, or does the fact that you are the person generating the movement matters? So is it a matter of the movement, or is it the person generating the movement which matters?
Thank you very much. Actually, we didn't get the data that allow us to make this judgment, but from comments from our participants and subjective results, we could know that, for example, when like we can see that when we were working, we had the decrease in performance for accuracy and recognition time, and we think that the movement made by the body when moving can alter the movement of the finger, because to feel the texture we have to make swipes in the surface. Also, our experiment for the working activity was in an outdoor context. So we think also that the main reason is the attention of the user, because the attention is directed toward other tasks. For example, like users have to get alert to the environment, because there is a lot of other people that are working, and also to stay alert maybe for stones or trees when working.
Mm-hmm. All right, thanks a lot. Unfortunately, we need to move on a little bit. Sorry for that. So, more questions perhaps than in the Discord channel. Sorry for that, to interrupt you. Because I would like to also allow a question for the other papers. Subtlety to Nikolai. Question is here. Again, very nice work. The vibrotactile feedback was evaluated at the best one. Did you consider multimodal feedback, e.g. visual feedback and vibrotactile? So this is what other people also try to do, and perhaps you can comment on that. Nikolai, please.
Yeah, We did consider combining different modalities in our work. However, what we present here does not cover that, because golf-wise, it feels like the visual cues would be more suitable to reflect the factors that are club-related more than just the posture. Actually, users commented that this ability to limit their visual attention from like looking at their own body parts was good for them, so they can focus on the ball and on the club, so how they do the impact. But definitely there is something to it, and we believe that if we were to design the system that would holistically support golfers, combining these two is very likely to be a successful endeavor.
Good. All right. And Konstantin Klamka is asking, do you think that your setup could also help people in other sports? Since I can imagine that the posture awareness is also important for many other sports, like tennis, for example. And I extend that question a little bit. Jorge is also asking whether it's possible to use it maybe for completely different things, like dentists or surgeons working in medical applications. So how can you generalize your approach, your findings to other sports or domains?
Well, we believe that our results and our insights are directly applied to semi-stationary activities. So this happens in different sports like archery, long distance shooting, and many other. And to these, they can be applied with just some domain-specific adjustments.
Mm-hmm.
When we considered more dynamic movements or those where the subject does move around, we went in this scope. We are inspired by the work done that was presented at the Chi 19, where there were soles for the shoes, which were capable of measuring the weight balance. And we believe that combining our technology and our insights with these findings could provide a successful tool to support more dynamic movement arrangements.
Right, thanks a lot, Nikolai. And to the last paper, to Paulo, a question. It's great to compare really like that, these different interaction modalities or devices. And my question, however, would be, how can you really generalize that? Isn't that very dependent on the device you are using, like a VR headset versus an AR headset, a small mobile phone versus a tablet, perhaps for interaction, and also dependent on the context of the task, basically, because you had a particular task which some of the devices, for example, are better suited. You can turn it around to position a Lego block, but perhaps if you have a bigger object or some different task, it's not so nice, the mapping. So maybe you can say a little bit about the dependence on task and device type.
I think you have the clue, and some of the discussion and conclusion we have are exactly on this direction. So first, of course, the interaction itself depends a lot on the device that we have. And in fact, some of the idea that we have could be that we could try to do the same interaction, but everything in a virtual setup. So we could try to do the dragging gestures, the movement gestures, and the directly holding, but all in the same HMD environment. And in this case, you could in some way remove the device effect and really evaluate the interaction by doing always in the same setup. This is one of the ideas that we have. The other one, of course, is a question that makes sense. And one of the conclusions that we get is that actually, depending on the money, depending on the task, depending on the space that you have for mounting the system, of course, one system is not going to solve everything. And in some cases, the mobile phone will be a very good device. In some cases, it will be not, depending on the precision that you need, on the kind of movements that we have, on the volume of the area in which you are working. And actually, even the users themselves, they say that, okay, most of us prefer the HMD, but we recognize that the setup of the HMD with the cameras and the tracking is very complex and very costly. And so in many other positions, probably the other setup that we didn't like that much would be enough and would be even better. So of course, depending on the task and on the problem we have, there is not a single solution that will work, and you will have to use the different one. And actually, one of the main conclusions that we have is that one was much faster, but they were able to do the task with all of them, and all of them were not so bad, let's say. So depending on the task, you can just say, maybe it's better not to be so fast, but to be cheaper, or to use something that somebody already know. And these are things that you have to consider when you are developing the system.
All right, thanks a lot for all the answers. I have to cut the session at this point because it's a follow-up session. I do thank you very much, and there are more questions in the Discord channel, and some of them are already answered by you, and I hope you can continue engaging in a lively discussion. It was a great session. I enjoyed it very much. So thanks to all of you. A virtual round of applause. And I also have to draw your attention, even though this was the last paper session of ISS today, we still have 3 exciting more sessions. One is a town hall meeting, which just starts at this very moment